units of measurements were based on parts of the human body, such as inches, spans, cubits, feet and yards. Others were based on human activities, such as bushels, stones, acres, pints and miles. But these human measures varied from person to person, and those based on traditional activities varied from place to place. Measures needed to be standardised across the country, and accurate versions kept in a safe place for reference. Here in the Science Museum collection is a set of 500-year-old standard measuring jugs from Tudor times. That's a gill and that's a pint. This is a standard yard, and this is a standard £1 weight. As trade between different countries increased, universal standards of measurement were needed. From the 17th century onwards, Britain had an empire that stretched around the world, so those countries used the British imperial measures of feet and inches, pounds and ounces, gallons and pints. But with 12 inches in a foot, 16 ounces in a pound, and 8 pints in a gallon, and the rest, these imperial units were quite awkward to do calculations with. But across the English Channel, something exciting was happening. In 1789, there was a revolution in France that overthrew their government, executed their king, and took over power from the ruling classes, cutting off many heads in the process. The new revolutionary government wanted to change every aspect of French life, and one of those changes was to introduce a completely new and rational system of measurement, which would be based on something far more scientific than the length of someone's foot. So the French Academy of Sciences came up with the idea of a measure based on a 10 millionth part of the length of the arc around the Earth at sea level from the equator to the North Pole. That would be their new unit of length, and they would call it a metre, from the Greek word for measure. It took French surveyors and mathematicians several years to work out the exact length of this new metre, and when they had, an accurate metre bar was made in platinum and kept in the French National Archive as a permanent reference. Here's a copy of that standard metre bar in the Science Museum collection, made of brass. The French Academy came up with more units based on their new metre. The unit of volume would be a cube of sides exactly 1/10 of a metre, which would be 1 litre. And the mass of 1 litre of pure water would be 1 kilogram. What's more, all these new French metric units would have larger and smaller versions based, logically, on multiples of 10 to make it easier to convert between them. They were all given logical names. So 1 kilometre is 1,000 metres, 1 kilogram contains 1,000 of these tiny grams, there are 100 smaller centimetres in a metre, and 10 even smaller millimetres in a centimetre. In their revolutionary further, the French went even further, and in 1793 they proposed a system of metric time based on a 10-day week and a 10-hour day. But would this new rational system catch on? Well, not surprisingly, it wasn't too popular with the people of France. The new decimal calendar and the 10-hour clock was forgotten about after a few years, but the other metric measurements eventually began to catch on in Europe. It was only when Britain joined the European community in the 1970s that our old imperial feet and inches, pounds and ounces started to be replaced by European metres, litres and grams, though we still hang on to our miles and our pints. So where did algebra come from, with all those equations with their x's and y's? In fact, we didn't have x's and y's until about 300 years ago, but solving problems with unknown quantities has been around for thousands of years. In ancient times, what we call equations were word problems involving quantities such as length, weight or money. There's a famous Egyptian mathematical papyrus from about 1650 BC called the Rind Papyrus, and in it there's an example of an equation. It says, if a quantity plus a quarter of it equals 15, what is the quantity? We could write this problem as an equation, a quantity x plus a quarter of it, 1/4 x equals 15, and then work our way through it to get x equals 12. The Egyptians had a different method. They'd guess. So let's guess that the unknown quantity is, say, 4, plus 1/4 of it. That's 1, making 5 altogether. That's 3 times too small, so let's make the unknown quantity 3 times bigger. That's 12, and try again. 12 plus 1/4 of 12, that's another 3, equals 15. Correct. The trail takes us next to Persia, that's present-day Iran. The father of real algebra is the 9th century Persian mathematician Al-Khwarizmi. He wrote a book about solving problems with unknowns, and it was called The Compendious Book on Calculation by Completion and Balancing. The Arabic word for the completion is al-jabra, which is where we get the word algebra. And a lot of algebra is still about completing and balancing equations. In his book, Al-Khwarizmi was the first mathematician to set out some standard methods for finding an unknown quantity in an equation. He gave the example of what we'd write as x squared equals 40x minus 4x squared. Al-Khwarizmi explained how to get all the similar terms together, in this case by adding 4x squared to both sides of the equation, and how to simplify it by adding, subtracting or dividing by the same quantity on each side of the equation to keep it in balance. In this case, dividing each side by 5x gives the answer x equals 8. Al-Khwarizmi's method is exactly the way we simplify and solve equations today. So, in this book, written over 1,000 years ago, Al-Khwarizmi laid out all the basic principles of solving equations that we use today. In the years that followed, Al-Khwarizmi's algebra came to Europe, but mathematicians still worked in words, like this problem from the 13th century Italian mathematician Fibonacci. The cube and 7 things less 5 squares is equal to the root of 6 more than the thing, with the thing being the unknown quantity he's looking for. Over time, mathematicians developed shorthand ways of writing out these problems. This is how Fibonacci's cube problem might have been written 200 years later, with m for minus and p for plus, a dotted line for equals, and CO, short for cosa, Italian for the unknown. But with each mathematician using their own shorthand, these equations weren't easy to understand. It wasn't until the 17th century when French mathematician Descartes came up with the idea of using letters from the end of the alphabet for unknown quantities that we finally got our familiar X, Y and Z. Now that these symbols have become standard, algebra is a universal language of mathematics which can be shared around the world and everybody can understand it. Well, almost everybody. Maths developed in Europe based on ideas from India and the Arab world, but long before that, from around 600 BC, the ancient Greeks had a mathematics of their own. The ancient Greeks had a clumsy and confusing system of numbers which used all the letters of their alphabet and no zero, so they found calculations hard to do. The Greeks preferred to think of mathematics in terms of lengths, areas, volumes and ratios, and would discuss it in words rather than write it down. They called their mathematics geometry, earth measure, and most of the geometry we do today comes from the ancient Greeks. Like many civilizations before them, the Greeks knew the importance of maths for trade, building and navigation, but to them maths was really a philosophy, a way of thinking, which was important to study in its own right. It wasn't enough for the Greeks to know that something was true. They wanted to know why it was true, and if it was always true. They wanted to prove things, and it's this idea of proof that was one of the most important mathematical ideas we got from the Greeks. One Greek mathematician whose name we all know is Pythagoras, who lived in the 5th century BC. We know about Pythagoras because of the famous theorem named after him about right-angled triangles. It says that the square on the side opposite the right angle equals the sum of the squares on the sides containing the right angle. Today we write this as a squared plus b squared equals c squared. But the Greeks used actual words to describe actual squares sitting on the side of an actual right-angled triangle. Pythagoras wasn't the first to appreciate this special property of right-angled triangles. The ancient Egyptians used rope with knots in it, or wooden set squares with side lengths such as 3, 4, 5 or 5, 12, 13, which they knew from experience would give them a right angle. And this Babylonian clay tablet has a diagram of some right-angled triangles. But it was Pythagoras and his followers who proved that this theorem was true for any right-angled triangle. He considered 4 right-angled triangles that make a square and contain another square, and described how to move them about in various ways to prove it. There have been hundreds of other proofs since, but Pythagoras' theorem is still one of the most important, useful, and elegant in all mathematics. Another well-known Greek mathematician is Euclid. Around 300 years BC, he wrote, probably with others who worked with him, a remarkable series of 13 maths books called the Elements. They were written on papyrus scrolls, so there's nothing left of them. But Euclid's work has been copied and translated from one language to another, right up to the present day. Here's an English translation in 3 volumes. And here it is on the internet with interactive diagrams. There had been mathematics books before, but Euclid had a unique approach. He began with a few agreed definitions, like the ends of a line are called points, and some basic assumptions such as things which equal the same thing also equal one another, and then used them as the starting point for his proofs. In the Elements, Euclid covered all the mathematics that was known at the time, the fundamentals of geometry, the properties of triangles, circles, and 3D shapes, ratio and proportion. He started with geometrical constructions that can be done with a straight edge and a pair of compasses. And here's the first one, Book 1, Proposition 1, how to construct an equilateral triangle. Something we still do exactly as Euclid described. And when you're doing circle theorems and you notice that the angle at the circumference is always the same, you can turn to Euclid's Book 3, Proposition 21, and here it is. In a circle, the angles in the same segment equal one another, which he proved 24 centuries ago. In his Elements, Euclid's whole idea was to start from something simple, agreed and known, and then build on it logically step by step to prove something far more complicated. Thanks to Euclid, the idea of rigorous mathematical proof based on logical thinking was born, which is still the basis of modern mathematics.